Many people think of glass as fragile and delicate. Others see its strength and power as a material. But what if something was able to exhibit both of these properties? This is a Prince Rupert's drop. When hit from its base, it seems almost indestructible, but with the slightest pressure to its tip, the whole thing shatters. Prince Rupert's drops can be made by dropping molten glass into water to be rapidly cooled, but what about this simple process makes such a unique physical phenomenon? The answer to this question lies within the internal makeup of the drop. In 1994, two scientists investigated this using high-speed photography. Their findings demonstrated how compressive stresses pushing inward and tension forces pushing outward led to a state of unstable equilibrium, meaning any disruption to the drop's integrity would cause it to explode. When the glass is dropped into water, the exposed exterior begins to cool while the inside remains hot. A notable property of glass is that as glass is heated, it expands, but when it's cooled, it shrinks back down. As the outer layer of molten glass cools and shrinks completely, it forms a solid shape. When the inside of the drop later begins to cool, those molecules also want to shrink back down, but the structure of the drop has already been formed by the now cooled outer shell. Because of this, the internal molecules pull towards each other, creating incredibly high tensions, which become locked inside the glass as it cools completely. In a later study, the stress distribution in Prince Rupert's drops were tested using a polariscope, a device used to determine the stress or strain in certain materials like glass. This image shows a polariscope reading of a Prince Rupert's drop, where each fringe or colored band indicates stress in that area, with the more bands meaning more stress. This image proves the high compressive stresses around the exterior since the bands are depicted incredibly close together, and the tension inside is shown by the larger bands of color. This unique form gives the base, or largest part of these drops, a very high fracture strength, or ability to withstand huge forces, since you must disturb the interior tension zone in order to break the drop. When hit at the base, cracks form parallel to the surface, meaning they do not reach down toward that internal tension area. However, breaking the tail allows direct access to the tension zone, causing the drop to explode. The transformation of energy throughout this destruction process is also quite interesting. As the initial force exerted on the tail of the drop releases stored energy, shown with red arrows, a chain reaction causes the rest of the drop to feed off that released energy until it reaches the base. When the internal tension zone, represented in orange, is disrupted, the potential energy stored within the glass explodes, which rapidly releases kinetic energy outward, shown in green. Think of this like a domino effect, where pushing one domino down affects everything beyond it. Prince Rupert's drops are such incredible structures with loads of phenomenal physics principles hidden just below the surface. Thank you for watching.